In today's lesson, we're going to talk about how light interacts with matter. The first way that it interacts with matter is through absorption. Matter can absorb light. An opaque object, when it absorbs light, you can't see through an opaque object, like a brick wall. So when light hits the matter, all of the light is absorbed. In a transparent object, on the bottom, transparent is the opposite of opaque. A transparent object, all the light passes through. And when I say all of it doesn't actually pass through. Some of it gets absorbed by the molecules in the transparent material, but you can see light clearly through it. What you can see is on the other side. It's a clear picture, so the light waves don't get absorbed very much at all. And then the translucent object, some of the light will be absorbed. You can't see objects clearly, but the light does pass through. You can see shadows and shapes and things like that. So here you can see translucent object like a lemon or an orange, right? When you shine a bright light through them. Window covers, light covers, shades, any kind of lamp shade, those are all translucent objects. Air is a transparent object, so you can see objects clearly through air. Here we have some pristine water and then a piece of glass. Another way light interacts with matter is it reflects off the matter. Reflection is when light strikes a matter, or a wave, I shouldn't say light, a wave strikes matter and it bounces off. The reflected wave is always at the same angle as the incident wave. So this is known as the law of reflection, where we say the angle of incidence is always equal to the angle of reflection. The angle that the incident ray, and that's the light coming from the source, and then the reflected ray would be the light coming to your eye. Whenever we measure angles in geometry, we always measure them off the normal, which is the perpendicular to the surface. So here you can see the pink shaded I and the blue shaded R. That's the angle of incidence and the angle of reflection, and they're going to be the same. On a still lake, down there in the bottom picture, you can see a really good picture of reflection. You can see that some of the light is being absorbed. It's not perfectly clear, but it's very close. A diffuse reflection would be if that lake were choppy. If the lake were choppy, now we don't have a smooth surface where all the rays strike parallel and then they're all reflected parallel. What we have is a bumpy surface where those incident rays are all coming in parallel to each other, but since the surface is uneven, now the rays are bouncing off at their own unique angles. On the top left picture, you can see the sun being reflected with a specular reflection, which would be a regular reflection, and you can see the image is very clear. And then below it, where the water is moving, you can see how the moon's reflection in the water is now like a column, because it's being reflected to our eyes from many different angles. It's not just one angle. If that was a perfectly still lake, you would see the circle of the moon like in the picture above it. And then on the right, light does pass through trees because light is being reflected off the leaves. It's not all being absorbed. So you do get light when you're under a tree. When light strikes a mirror, it creates a virtual image. And what a virtual image means is that the image is being or looking like it's on the opposite side of the mirror. So where Nelson Mandela is looking in the mirror, that's a virtual image, and he is as far away in the mirror as he is from himself. He appears. So the distances are the same. So let's say he was a foot away. That means the actual image of him in the mirror and himself would be 2 feet apart from each other, because there's a foot of depth in that mirror. In a planar mirror, that's a flat mirror, and flat mirrors produce virtual images. We also have convex mirrors. Convex mirrors are curved outward. You can see a very good picture of a convex mirror like in a department store. In the department store, you're going to need to see a wide angle so that you can see if there are shoplifters and such. So what happens is the image gets smaller, and if you look at the geometric drawing at the top, you can see that the image is smaller than the object. And that's one of the characteristics of a convex mirror. We use them to see blind spots in our cars. A truck would have a circle mirror there where it can see the whole blind spot. Sometimes in your car you just have a mini circle or one like this mirror here. Sometimes you put them at sharp turns so you can see around the turn, or at the end of a driveway you would put one so you can see traffic coming in both directions. In hospitals, they have convex mirrors up at the corners so they can see if someone's being pushed down the hallway on a gurney at a high rate of speed before they get to the corner so there's not a collision. Opposite of a convex mirror is a concave mirror, and a concave mirror produces a real image. That's an image on the same side as the mirror. So a concave mirror makes the image look larger, and you see how if it's inside the focal point, the object, that it makes the image upside down. It inverts the image. So a lot of it has to do with focal points. And you can see if you take like a spoon from your kitchen and move it back and forth, you'll see where the focal point is. When the object goes upside down, it's outside the focal point, and when the object is right side up, it's inside the focal point. So the idea is makeup mirrors magnify. Concave mirrors magnify. Dentists use them to look at your teeth. We use them in satellite dishes. Satellite dishes receive a signal, and then they magnify that signal and send it to the receiver. Those are concave mirrors as well for sound waves. Another type of interaction is a refraction. When a wave hits the boundary between two medium and some of it goes into the medium, it can refract. This only happens if the wave is at an angle. If the wave is going in perpendicular to the surface, it'll all go through without refracting. The reason that it refracts is that part of the wave is entering the slow material before the other part of the wave. All materials have an index of refraction, which is basically telling you how much friction is there. So if you have a higher index of refraction, you're going to go slower than if you have a low index of refraction. So if you look over here at these yellow balls, we'll call the mud the high index of refraction, the pavement the low index of refraction. So when the bottom set of balls hits the mud, you can see they slow down. And since they're attached to the one across it, it's still moving fast. So the slower ones slow down before the outside wheels, and that causes this refraction. Like if you're driving your car down the road and there's a puddle on the right-hand side of the road and your car wheels go in that puddle, it pulls your car to the bank because two of your wheels are going slower than the other two wheels. And that's what causes refraction, when half of the wave or part of the wave is going slower than the other part of the wave. You can see here our incident rays. If you're going from something with a high index of refraction to a low index of refraction, we bend away from the normal. And if you're going from something with a low index of refraction to a high index of refraction, we bend towards the normal. One application of this is total internal reflection. You can see in the bottom right-hand picture that as our angle reaches what we call the critical angle, when it reaches the critical angle, none of the wave will be able to be refracted out of the medium. So all of the wave stays inside the medium. So at this critical angle, the wave will not leave the medium anymore. It'll stay inside the medium, and this creates total internal reflection. So the light will stay inside and it won't get out. Diamonds are cut at certain angles to create this effect of a sparkling diamond. So the light gets into the diamond, it bounces around inside the diamond, and it can't get back out again. The only way it gets back out is through the top, and that's what creates all that glitter when you look at a diamond. Diamonds have the highest known critical angle of any known substance. Some more applications of refraction. You've probably seen a straw. Looks like it's cut in half in the water. That's an application of refraction where the light is moving to your eye at a different rate of speed. The fish, you can see the actual position of the fish and the image that you see by your eye. Your eye is looking straight forward. It thinks it sees its fish right there, but the light from the fish is actually refracting away from the normal. So the fish is below where you think you see it. So if you're going to try to stab a fish with a spear or grab the fish with your hand, you always want to aim below the fish that you see. Another thing that restaurants and bars do is they use mugs with a thick amount of glass, so it looks like the liquid inside the mug goes the entire edge of the container, but actually that thick amount of glass refracts the light outward from the liquid, and it makes it look full when there's actually a thick bit of glass there, so you're not getting as much as you actually think. Some applications of refraction, some more mirages. Again, you're looking down. Since waves move faster in warm air rather than cold air, what happens is you're looking down and the waves are being refracted up to your eye. So you look down, you think you see a tree in a pool of water, and what you're actually seeing is a mirage, because there is no tree in the water. Your eye and your brain just says, oh, there's a reflection of a tree on the ground, there must be water up the head. Sometimes you'll see this on a hot paved road. In the summer times, you'll see those heat waves, we call them. That's a refracted ray. Sound also refracts. On a cold day, sound is going to refract downward. On a hot day, sound refracts upward. And this has to do with the air temperature. On a cold day, the ground is cooler than the air above it, so the air above it is moving faster, and this causes refraction downward. On a hot day, the air on the ground is hotter than the air above it, so sound refracts up. If you ever played football, you know that in the fall, and in the beginning of the fall, when it's still August, the stadium doesn't seem quite as loud. That's because the air is warmer and the air refracts up out of the stadium. In the winter, when it gets to be November and you're playing football, the air on the ground is cool, so when all the fans are cheering, the warmer air above refracts the sound downward into the stadium. So that's just one application of refraction. Sunrises and sunsets do with the Earth's atmosphere. You think you see the sun on the horizon, but it's actually already sunk below the horizon. The waves coming up from the sun are being refracted in the atmosphere before they get to your eye. The final thing we're going to talk about is dispersion, and we mentioned this already, that white light gets dispersed into the rainbow of colors. So white light enters a prism, it gets dispersed, or it separates because all the different wavelengths refract at different angles. Red with the longest wavelength refracts the least, violet refracts the most, and this separates the colors into the visible spectrum. Violet is reflected the most, that's what gives us our blue sky, and red is reflected the least, that gives us our red sunsets. So just before the sun has sunk below the horizon, you're going to have that red that's barely refracted at all, and that's what creates that glow. Rainbows are a product of dispersion. What happens is the white light enters the raindrop, it separates, and then it reflects off the back of the raindrop, and then it comes out upside down. The red is going to be at the greatest angle, and the violet is going to be at the least angle. So that's why red is on top of the rainbow. You have to have sunlight behind you and water droplets in front of you to create a rainbow. Also, some of that light sneaks out the back of the raindrop and hits the raindrops behind it. And that's how you can form a double rainbow. Notice how the double rainbow is inverted. The red is on the bottom. And it's less intense as well. And this is because less of the light is being seen, because as it goes out the back, some of it's being absorbed and sent back out, and some of it's being reflected. And that is essentially how rainbows are produced.